Now Oleg will tell us about how free variables are in effect.
Yes, so welcome to the last HOPE, so last talk of the HOPE'23. The summary of the talk is it's kind of a work of progress report, but there is some prototype, so there is some code that works, and there would be a demo of it. So it's about seemingly more unexpected, a seemingly practical application of some theoretical curiosity. I mean, for the way of writing compiler with kind of incremental diagnostics and easier variable usage and some analysis. So it's an abstract that's kind of, nice, but you kind of think it's kind of off the wall. Why this, and how I come to that, and, what's the meaning of it. So, some motivation is in order. So as a background, as a motivation, so last fall I was teaching a compiler class. So the source language is some dialect of Tiger, so something like Pascal, or you can think C, but with nested functions. And the target language is assembly, and so the point is that it produces the code that can run on students' computer, the Windows or Macintosh. And there was a meta language, everything was written on Camel. So of course that this is a compiler class, probably everybody in the audience taught something like that, right? Because it's step one. But my classes was completely different from anybody ever taught. So there are two, main differences. So the first of all, it's incremental. So it's not like, parsing and then, type checking, code generation, and so for analysis code generation. So it's kind of horizontal. So we started with a language that contains only integers and compulsory x86 code, which is, by the way, there's already non-trivial. There are some, edge conditions into here. Then we had expression, then we had all the things, and then we had the nested functions and mutually recursive and so forth, so forth. So each time, so in each step is a complete compiler from the subset of the language to the working code. So, everything, every step, so in each class that we add things and then, get from one compiler to the bigger compiler, but it's also a complete compiler and you can test it and so forth. And testing was also a part of that. So, and another thing which is completely different, I don't think people tried it, it's written completely in Douglas final style. So what it means in a basic, so there is no AST in a conventional sense. And also there is no copy-paste. So there was, each step was the reuse of the previous code. And by reuse, I don't mean, like copy and then add something. It means the previous step was a compiled code. And the new code use this compiler, not source code, I reuse this compiled code without recompiling it. So only Lex and Yak, unfortunately cannot work because part of the course I wanted to teach Lex and Yak as it is, so I couldn't do it my own. So adding a new feature, each step, most of the things is just, I said, the reuse or include in camel terms and adding a couple of definitions, actually, oftentimes a couple. But there is a couple of, twice actually occurred, then reuse, you kind of, reuse the old code, but you redefine all the contents of this by redirection. And it happened only twice. So once at the early when they introduced type checking, and there was the second way. And guess, I don't know when that happened. Well, that happened right in here. And actually, this part required 2 lectures for the local variables. Well, one part because when you introduce local variables, then you introduce memory, and then it's all the things about memory allocations and all this, trouble to explain it. So, local variables, variables is a problem, but, we know how to deal with it. So if we have variables, then, we introduce environment or variable assignment. So, we call, mapping from a variable name to, to whatever it denotes. Well, everybody does this, and, everybody explained. And while I was preparing the lecture, I realized, there is another way. And actually, I even myself thought, I mentioned it, I hope, 6 years ago. And wrote even a paper about it, about theoretical, but it's all kind of theoretical paper. So during the class, I said, well, everybody hears this what you need to know because everybody does introduces environment. But by the way, there is another way. Well, I mean, it's not the only choice. And all of a sudden, one student raises the hand and says, what's the other way? I mean, I should say that in Japan, students hardly ever ask questions during the lectures, even after, I mean, me repeatedly prodding them to ask. So I thought, well, it's a good sign. I mean, for the first time ever happened, some student asked questions. So I mean, I explained something, but I was very disappointed in how I explained it. And to atone for that, I wrote a web page, I mean, kind of tutorial explaining what's the second approach. And the point was, yes, it's the second approach, and it's kind of essentially that give the same results that's the environment. So, but as I was writing this web page, I realized, well, although essentially equivalent, yes, the results are the same, they are not actually exactly the same. There is a difference. And in the difference, which is in the hindsight is obvious, but it's kind of very rarely talked about. And also has a very nice properties that, I mean, kind of has a promise to solve some kind of my vexing dissatisfaction with the whole approach. And so this is the talk is, I mean, it's about this difference. So what is this difference? So to kind of introduce it, I introduced in a very primitive example. But incidentally, this example, although it's, I mean, very primitive, simplified, kind of follows the outline of the course that, I mean, I've done. So we start with well, we first write an interpreter. Well, we later on, because we're interested in a compiler, we'll later change it to the compiler, but we start with the interpreter. And well, the source language, the concrete language, you can see what it is. It has integers and it has addition. So that's it. So, and it's written in grammar in a YAC style. Well, that there is some kind of int and add happens. So what those? Well, I mean, if we, I mean, these are semantic actions, and I mean, if we arrange them by the types and the signature, that's what it is. And well, that is actually abstract syntax tree, right? So it's an abstract syntax of the things. Well, I mean, so what's the implementation of it? Well, one of the implementations, well, I mean, the ones that you can think is the domain, value domain is integer, representation domain is the same. Well, I mean, addition, there's only for the add, I added this printing of the result. Actually, that turns out to be important. I just want, I mean, for the point of the presentation. Well, the language is way too, I mean, simple. We want to add variables. And how we add variables? Well, by the way, we added to abstract syntax, we include the, type and add, variables. So I won't talk about, well, we're adding variables, so it takes name and kind of interprets it something. And there's also a let, because to introduce variables, but in the rest of time, I would skip this. So we'll talk about variables. Well, adding variables, everybody knows, right? So we introduce environment, which is, well, an associative list name to what the variable denotes domain. And, well, there's some lifting. And so, int, so essentially have to lift int, and we have a lift add to the, to the new domain. So you can see that I said that you kind of use the previous interpretation and lift it wholesale. So redefine all the definition by referring to the previous ones. So that's what, how it occurs. Well, again, it's everybody knows how it works. But, to demonstrate, okay, so who is it? Okay. So this step one is that a language with only integers, right? So we can say add integers and addition, add 3 and add 4, and then eventually finished. And I said that there was the intermediate printing, right? So you can see it actually kind of works like a desktop calculator, right? You add plus something, and then it immediately prints the result. So actually a very good model of desktop calculator, actually works even better than the tutorial in OCaml, example in OCaml tutorial. Okay, so that was the original, but now step 2 is that's added with the extended with the variables I just said. So let's try again this example. 1 plus 2 plus 3 plus 4. Well, nothing printed, right? And then we add finish, and then it's printed. So there is actually a difference. In a, well, kind of, I mean, I know before that, with environment, we see the intermediate results, right? I mean, here there's, I mean, the same example. Well, of course, this doesn't handle variables. This actually can handle variables. So it's actually a bigger thing. Yes, it's actually a good thing. But that also, when we introduce variables, we lost something, right? So we cannot evaluate, I mean, although we could, we cannot. Well, why is that? I mean, why is that happens? Well, so evalint was kind of like desktop interpreter. It interprets as was parsing. But eval environment interprets after the program parsed. Well, why is it? Well, so if we have a source expression 1 plus 2, then eval interpreter, the denotation is 3, right? Because this denotation 1, 2, and just adds them. Well, in environment interpreter, the denotation of 1 is, well, functional environment to 1, right? Although it actually, the denotation 2 is the same function. And the denotation of plus is function from environment to, I mean, to this bigger thing. Right? So it's, and you can actually see that 1 plus 2, and here's kind of 1 plus 2. Right? So it's what's the denotation is essentially the same expression where it was, but I mean, with all this extra garbage in between. But what it means in runtime, so we essentially build a closure which reflects the structure of the original expression. Right? So this is the AST, but very inefficient one, right? Because it's done using closure instead of data type. So, I mean, although I wanted to get away from AST, but actually, I mean, although I didn't get away from AST, and I also implemented inefficient AST. So that was my, I mean, a very big disappointment about this. And so, I mean, to kind of, and the difference, I mean, was my theoretical curiosity. It turns out it seems to have a promise to, I mean, resolve or alleviate my disappointment. So a different way of using the variables as well, it's like, well, free effect or reader effect, right? So if we're looking at the expression 1 plus x, and what's the denotation of it? Well, the denotation of 1 is, well, 1. And the denotation of x, well, there is some, I mean, we don't know. Okay, then, so the denotation of 1, it would be the answer. So A, we know what it is. And the denotation of variable, well, we don't know what it is, we ask. So here's, I mean, a name, and say if somebody can answer with a number, then we can continue, maybe ask another questions. So that's the denotation of the expression. And so the different interpretation of the same language of with the let, well, there is also let, but I mean with the variables is, I mean, I don't know, well, things like I mean before, but now lift and answer have a different meaning. Okay, so let's, I mean, I don't know, look at okay. So now it's actually look at the demos. Okay, here is the, I mean, bigger demo plus 4. Okay. Well, 1 plus x, then of course we cannot, I mean, I don't know, work on that. Now we have to wait. So it's kind of when variable occurs, then we have to kind of wait. But I mean, I don't know if before we could do something, I mean, for example, do it right away. So there is a difference between environment semantics and this effectful semantics. So the results are the same as before, but there is some, I mean, I don't know, promise to do intermediate results as, I mean, as the parse. So, well, of course, that, I mean, I know, yes, I mean, I know it's not the whole, I mean, hardly anybody is interested in writing interpreters or doing this, but, I mean, I know, there is, what the example shows that, so there is some sort of incremental evaluation as before, can handle variables, and AST can be, well, I mean, to some extent possible, I mean, reduce as it goes. So it doesn't have to construct the whole AST to represent the whole program. So it can, if it could reduce it, then it actually could. Well, I mean, again, so this is a very simple example, but you can see that promise. So it's actually possible to do it. And in environment semantics, it's just completely not possible to do it. So it seems to be worth investigating further. So, well, because this is a hope, I mean, I can't avoid, have some kind of higher order. And, yes, we can introduce functions. Well, here are the functions like all top level, and the body has to be closed. But we can also make, nested functions and bodies open and so forth. And actually, I not only can, but actually I implement it in the code. And but I skipped the implementation for the for the reasons of time. So, but again, we're interested not in interpreters, but we're interested in compilers. So, well, we turned interpreter and the compiler. Well, for the for the first language is actually very easy. So we used implementation, the same signature, but implemented differently. So the semantics domain nowadays, instead of integer, it's a sequence. Well, I'm now compiled to WASM instead of x86. So WASM is actually hip nowadays. So it's a sequence of WASM instructions that leaves the result on the stack, right? So that's the denotation of the expression. So int, well, it's a constant instruction that it leaves the result on the stack, and add is, well, use execute x leaves the result on the stack, y, and then put add, and then keeps the result on the stack. So it satisfies the condition. Well, and there are some, some other things. Well, adding, compiling for the variables and for the functions is a little bit more complicated, but, can be done. So let me give show the main demo. So the attraction of the approach is that performing analysis. And in a paper submitted, I showed some simple analysis for the usage variables. And this is analysis is needed if we want to allocate memory or local variables for the local things for the local variables. And it's easy to modify the analysis to, for example, check for leaf functions, which is also important for the compilation. But analysis is kind of explaining analysis and showing analysis are kind of boring. It's hard to get people excited about analysis. It's it's not visual. So for the presentation, I chose a different, not written in a paper, different demo. So, and let me demonstrate this demo. So it compiles. So that's the function that we maybe. Okay, this probably looks better, right? So we wanted to compile function f and then function g, so set of the function. So and well, so this is actually correct thing. Well, it was a correct program, and it compiles into WASM module. So if you, know WASM, then, it's well pretty printed a little bit ugly, but well, it's not for humans. So that's the start function, which is that corresponds to f of g. So indeed, put some kind of const 1, and then calls g, and then calls f, and then function g, takes the, get from the argument, and then adds some, stuff. So yeah, it looks like, does things, and actually you can really, run it in a browser using what, so it's actually runnable code. So it does compile things. So, but actually before that, okay. But the point of the example is as follows. So here's the OCaml code corresponding to, well, to the function that I'm reading, right? I'm doing. And it has some error, right? And actually has 2 errors. So, this is a kind of representative example how it happens or how it happens to me oftentimes. So, write code, actually oftentimes refactoring code. And you refactor from top to bottom, right? So here I kind of finish the function, but there are some problems into that. And here are the part where I am not finished yet. Kind of did substitution. And so if you try to compile this code, okay, OCaml C, minus C, test f.ml, then which error you get? Well, you get, invalid literal 1x. You get the syntax error, which is down, which is kind of, well, you can see by the errors. So first of all, it reports syntax errors. And then it reports the type errors, right? And then, if you fix the type errors, then it reports error in the generator or some analysis of it, if it's any. So, but it's kind of disappointing. I haven't, paid attention to that. I wanted to see the errors here instead of having errors there, right? So I wanted to kind of, if it did with this expression and it passed, then it probably, well, no serious errors anymore. So I wanted to kind of all errors to be reported as it goes. And let's see how this example works. Okay. Okay, so so first I'm going to put one definition. Okay. Then I put the second line. And it's already set, well, type error that the function f requires 1 argument, but it's applied with 2. So it didn't actually wait it for the, syntax error. So in that, so it already said already wrong. I don't actually waste time. Even parsing the things. Whether it's correct or not. So yes, it's kind of, it's kind of misleading to say incremental type checking, but at least incremental type error reporting. So, to extent, it's possible to report the errors, then it reports right away. So it's kind of, you can see correspondence where we had this primitive example with integers. So if you can do it earlier, then it's actually possible to do it. And now with the compiler, if you can, find that something is wrong early, then you can, report early. But actually, it's not only reports errors, it does some kind of, a compilation and some arranging the code also early, for that when the expression finished, before actually waiting for the, so if there is some kind of problem, maybe in code generation or in analysis, it also would be reported early, but not in this example. Okay, so, so the conclusion is what we learned that, learn is kind of we already knew, but it's just kind of maybe didn't, think about that much. So environment semantics is the one that everybody uses. So the meaning is a function, right? And is a function, it's opaque. We cannot actually see what's inside. So, well, we cannot then see that. Therefore, we can, the only thing we can do with functions is to apply, right? So that's the building all those big enclosures is the only thing we can actually possibly do. Another thing with, with a function, because it cannot be applied, cannot be examined, is that, well, for the constant function from environment reported the constants. It doesn't actually need any environment, but we can't tell from the function whether it needs it. We cannot tell how many, how often it needs a function. We cannot tell anything, right? So it's completely opaque. But with effect, the notation is a little bit more observable. we can say, well, it's, it's not even a question. Doesn't even need any of this environment. And also, we can observe it as a handler, right? And the handler can, see what the questions are being asked, and so observe which variables are used and how often they're used. And so by observing them, we get kind of, well, not for free analysis, but we, right in the process we get information about variables used in this expression, which is crucial things because we have to do it anyway for the compilation, right? But here we kind of get it in the process of interpretation. So that, and of course, it's variable usage analysis, so forth. But well, that part I kind of mentioned in the paper, but in the, what we see just in the demo, there is another thing in the conclusion is that we get some incrementality in error reporting. Which is also indication that when we get incrementality in error reporting, it means that it actually doesn't construct the complete AST, right? So it actually, keeps AST, doesn't waste too much memory. So it tries to do things, as possible. So in the future work, well, I'm teaching this compiler class again starting in a month. So I was kind of very curious to, well, take these ideas and, run to the whole compiler. So we'll see what happens. Okay, thank you.
Okay, thank you, Oleg. Do we have any questions? Yes.
This was a very nice talk. Thank you. I have my question is sort of in two parts. So the first part, it seems like this gives you a structure where your compiler is kind of depth first. It goes from parsing all the way down to code generation before anything else happens.
It's a good intuition, yes.
Okay. Whereas typically you have kind of breadth first.
Yes.
Okay.
Yes.
I guess my question is more a practical question. Like, is this better? Do you actually want to go all the way through the whole pipeline before you've sort of type checked everything, expression by expression?
Well, it's, what can I say? That's kind of empirical question, right? So well, we shall see. How. One thing that I find it pleasing is that, well, I find two things. I wanted to try to see, the whole project, if actually tagless final can work to the whole compiler from the, well, kind of C languages and actually better than C because it has nested functions, right? Yes, it actually can do, all the way through, code generation for x86 with the nested functions and some, lots of other things, right? So it actually works. But there are some problems with this memory usage, as I said, right? Which is very dissatisfactory. And here there is at least promise of solving those memory usage problems. So to me, kind of, well, it's like still a vague promise, but well, worth investigating. So if it promise works out, it would be a good thing. So.
Okay, so if I can just make sure I understand your answer. Basically, your tagless final approach had this memory problem because you were creating closures to handle environments, but this approach lifts that memory.
Yeah, so if you use,
make it more practical.
Yeah, so if you use environment, well, actually, in approach using environment, well, applies not only tagless final because it applies everywhere, right? You write interpreter with environment, you essentially build the closures, right? So but we simply don't think about it. Well, in tagless final, well, it's kind of, if you try big program, then you kind of see that. But if you, write student exercises and writing environment, or writing interpreter, it takes environment as the first argument, right? So it indeed, it has to build a closure. So it has to finish the parsing. But say, okay, well, it finishes the, so in a sense, you do it twice, right? So the first parser has to finish the whole thing and build the parse tree, and then it convert the type tree, parse tree with this environment thing, and then eventually, performs interpretation. So it seems to be kind of, solve the problem that, exists anyway, but rarely paid attention, and I myself actually never paid attention to it.
Okay, thank you.
This is cool. So this reminds me a bit of the structure we've been using when we're doing partial evaluation with free extensions? Have you thought of using this to do partial evaluation as part of the compilation process?
Well, yeah, it's kind of, I mean, I know, obviously it's, I mean, I know. Well, I mean, I know, in a sense, the answer, right? So it is, I mean, I know, it's a fully known or unknown, right? But it's kind of, I mean, like in your free extension, right? Is the value known or there are some parts of unknown? But it's kind of what you just mentioned. I mean, well, the free monad, nobody thought about from the point of view of free extension, right? Okay, well, at least I didn't think about this, right? But I mean, it is, I mean, partially known data structure, right? So, in a sense.
Okay. Any other questions?
Yeah, very interesting. So there's an older technique called attribute grammars. I don't know. So this, I don't know if this makes sense. This kind of reminds me of that. Because that was basically about eliminating multiple passes, so, and also going depth first. So.
Well, it kind of depends on the scheduler you use for how the attribute grammar is scheduled, right? But okay, so once you mention depth first, yes, I mean, it is so in some of the scale. I mean, how, for example, if you implement it in Haskell, then it's probably how it, I mean, yeah.
Okay. Any other questions? Okay, well, let's take that as the last question of Hope. Thank you, Oleg, again.